Yeah. I put a few words here. So this is my understanding as my perspective on understanding a lot of characterization works we do. So as you know, we a large part of our efforts are devoted to the characterization. So we do the X-ray, electron, neutron, and all kinds of both scattering and also spectroscopy, but also the imaging. So I think now we have the experts in all kinds of fields. So there, in the future, we probably can actually communicate that so that we can have their information better disseminated among group members. So what I see the characterization is simply we radiate the material. So we probe the material by monitoring how the system interacts. So I think the key word here is interaction. So once we irradiate the material with some kind of a radiation source, either be it X-ray, electron, or neutron, the material will respond to this kind of radiation. So this kind of interaction will yield some kind of a signal that can be collected. So in the case of XRD, it's actually we're collecting their how much the intensity of their scattered X-ray and their in terms of X-ray absorption, we actually it's the absorption coefficient we directly measure, and then based on some kind of their fundamental physics and especially the physical picture of how this interaction happened, then we correlate the collected signal, either the intensity of absorption coefficient, and they collect this kind of signal with some kind of a physical property. And I think that's really the power and the amazing thing about the characterization. Through this kind of interaction, we understand what's inside the system. So for XRD, we through this interaction between X-ray and the electrons, so we understand where the atoms are. So that's the branch of the crystallography, and we know how widely crystallography is used in characterizing materials from simple systems like the rock salt, the first XRD experiment, to protein, to chromosome, to even larger or more complicated systems, which is based on the crystallography that utilizes the interaction between the X-ray and electron to tell us where the atoms are. So we know how they connect with each other, right? And we know where are the bonds and how they arrange themselves. What are the neighbors? What's the connectivity? Then we know the exact details of the whole system. And in the case of X-ray absorption, what we do is we measure the coefficient, but because based on the Fermi-Golden rule and the dipole or the quadrupole selection rule, and we can understand where those intensity comes from. Then we have the picture about, for example, the density of states, or we have their understanding of the covalency, how strong the covalency is, etc. So it's the same philosophy. That is, we always probe how the system interacts, and then we collect the data to understand what's really inside. So based on that, I think it's a very important thing is one, we really always need good data, right? So I think depending on the specific experiment, the sample preparation can vary significantly. So one sample preparation method that applies here may not be applied to other fields. So we need to specifically know what is really the good way to prepare the sample. Then we need to collect the good data. We need to have a good signal to noise data so that we can analyze them with confidence. And also we need to be equipped with the knowledge. We need to understand the physical picture, the physics picture behind those interactions, so we know what we are doing when we analyze the data, right? And then we can provide some meaningful information to the community and say what we learn from this kind of experiment and what kind of information we can provide to other people so that we can make the research go further. Okay, So that's kind of a general picture of my understanding of characterization, and I hope can be helpful to you to also understand it. Um, this is a slide I showed last time, so I think that's just some brief history with some anecdotes. Especially, I mentioned we have some kind of a remote connection with some big figures. Especially, actually, there John Hansen, who used to be actually in Jose's group at chemistry building, and he is actually the son-in-law of a Nobel laureate of Hauptmann, who in 1985 developed the direct method for solving the structure from the powder diffraction, so which was a really breakthrough at the time. So you can see from these figures, I think many of them you are very familiar with, and you can understand the importance of X-ray diffraction in advancing the science and for helping us to know things from the DNA to actually the vitamin B12. So which was actually characterized by Dr. Hodgkin in Britain. So all those figures shining in the sky of their science history and give us actually tell us how to do it, right? And the people also we can see the struggle they have been facing with. So it's barely how to solve the structure from powder diffraction is actually a long-standing problem and that their scientists have trying to deal with. So actually a lot of our Nobel laureates comes from this direction that people come up with different methods to really solve the structure from the powder diffraction. And for people like us who really do diffraction a lot, I think it's necessary for us to understand what's the challenge of the powder diffraction, right? So this slide is basically help reviewing what's the pros and cons for single crystal powder. I think you all are aware of that the benefits of single crystal, right? We get the 3D the diffraction pattern. So actually, we can collect up to thousands of diffraction peaks. And so actually, we have HKL and we have intensity. So we're basically solving a sequence of equations, but we have so many equations, so it's much easier to really solve the variables. So with a single crystal, we can solve the structure as complicated as a protein, right? Also, that's the basic philosophy of solving the structure of protein, that people always spend a lot of time growing the crystals of the protein and then do the single crystal diffraction on them to really understand where the atoms are in the protein, which can up to millions of atoms. And for the powder diffraction, it's barely for us who are doing the battery research. I think probably it's much more frequent one that we use in daily life, because almost all the materials we deal with are powder. But surely we're kind of talking about a single crystal NMC, right? So, and also, in fact, they're also single crystal like the lithium carboxide. But in general, I think the powder diffraction is the more frequent one used. And even in the single crystal, the quote unquote single crystal NMC, we're still dealing with like the 10th micron single crystal. Simply saying that they do not have the primary particle. Their primary particle is actually tens of micrometers. So that's kind of still kind of small if we really talk about the like millimeter sized the single crystal. So powder X-ray diffraction, I think, is the one we really want to focus on and understand how it happens and what kind of information it provides to us, how to do experiment, how to analyze data, and I'll discuss some of the applications that for the battery research. Okay, so for the powder X-ray diffraction analysis, I would suggest we look at the three parts, right? We understand them and approach this problem from three aspects. When we look at the XRD pattern, we probably see some sharp peaks, sometimes bumpy peaks, but we also see a background that is not very flat in most of the cases, some kind of curvy background where we see the peaks, and the peaks, they can have a different intensities. Sometimes we see strong peaks and some peaks are very small. And Also, their peaks have the unique shapes, right? Sometimes we see very symmetric shapes and really like them. They help us to model their pattern very well, but sometimes actually the peaks do not behave very well. We see the asymmetric shapes, and they're sometimes it will cause problems for us to fit the data. So we need to understand those aspects, the position, the intensity, and the shapes. And the process of understanding them, I think, is also the process of understanding the physics picture behind the X-ray diffraction. As I mentioned, so that physical picture is what we need to really interpret the data we have to actually to explain the interactions and their in terms of the information embedded in the system, right? So depending on how the progress we have today, so we probably just cover one or two aspects of them. A general overview is we actually talk about peak position. I think everybody is very familiar with the peak position. We talk about Bragg's law all the time, right? And we know the association between despacing and lattice parameter. And for the peak intensity part, I think probably that's lesser known field, since the peak intensity is actually not intuitive. It's not something that can be intuitively learned. We have to actually go into a little bit depth about how the intensity arise. And so we have to talk about the structure factor. We understand why this peak have this amount of intensity, and what are the influencing parameters, right? So sometimes when we see the intensity decrease, what could be the causes? So in that part, we talk about their atomic form factor. We talk about atomic form factor, and we talk about their systematic absences. So sometimes we see for some system we see only very few set of peaks, particularly for the high symmetry system. For example, the FM3 by M, right? So that's a very high symmetry cubic system. We probably only see like 4 or 5 peaks in the range of 180 degrees C for the copper K alpha radiation. Very few peaks, right? But sometimes we see a lot of peaks. For example, for the monoclinic system or for the orthorhombic system, we see a lot of peaks, right? So why sometimes peak appear and sometimes disappear. And also very important is actually the atomic position. So this is the basis of solving the structure. We talk about the solving structure. So what we're really doing, what we do is actually we want to identify the position of the atoms. And what gave us the right to do that? That's because we based the whole thing on this picture, this correlation between atomic position and the structure factor, which actually translates into the peak intensity. So that's why peak intensity is very important. That's the basis for us to really know where the atoms are. That's what the physicists and the chemists they care, right? So I think this is a non-intuitive picture, and we need to make them clear and hope everybody can understand it very clearly. Also, there are other factors like multiplicity, right? Depending on the system, the symmetric system we're dealing with. So different peaks can have different multiplicity. Also, we have the Lorentz factor, which relates to the radiation and also the detection geometry that we use. And also we have the atomic displacement parameter. So I think a very similar term that we use in the analysis of the Fourier transform exacts for the X-ray absorption is actually the Debye-Waller factor, right? So we fit some kind of a sigma square to describe the disorder associated with system. And similarly in XRD, we have atomic displacement parameter, and we discussed this a little bit also. And also we have absorption coefficient. So we know that whenever we use our radiation, so let's just talk about X-ray. Whenever we shine X-ray on the material, there's a cross-section for this specific material and this specific wavelengths. So we, like I mentioned, we always want to high quality data. What do we mean? We want to actually to remove ambiguities. And to do that, we want to actually make absorption as low as possible. And so when we mention this, I'll show a practical website, and that we can directly input the parameters for our specific system, so we can know whether the radiation we choose is reasonable or not. Okay, and also for the last one, the peak shape. Um, this is probably a little bit, how to say, that we meet less frequently when dealing with. But when you come to the point of fitting XRD data, and you really want to know what you're really doing, instead of actually using the black box approach, then you really have the motivation to understand the peak shapes. And so we are talking about actually the current approaches that is widely used in the diffraction community, including the fundamental approach, empirical, and the semi-empirical. And I really want to make a note here, because I think the BNL people made a lot of contribution to the semi-empirical approach, as I'll show in the slides when we come to that point. So I think that's something that we can be proud of as the contribution from the BNL to actually the whole diffraction community. Okay, so this is basically what I just mentioned, and we care about these three things, right? And the information from each of them is listed here. And so there is barely the peak intensity. So you see, actually, there's really a lot of information coming out from the peak intensity. So we really care about that, right? And also the peak width. And but also make a note here, which I highlighted in red. I can never emphasize enough the importance of data quality. With a good data, we can do many things. Without good data, we can only vaguely say something, and most of the times it's simply confirming or repeating what other people have already done. So I can never emphasize there enough time how important to prepare good samples and collect the good data. And also depending on how complex the material is, right? So if it's a relatively simple system with not so many atoms, then probably just we can use the X-ray diffraction. And if it is too complicated, maybe involving some like amorphous phases, then we start thinking about other approaches, right? Like a PDF or absorption or the TEM or the neutron. So, and we can try to expand the scope of the techniques. And also depending on the analysis approach we use, right? So I'll mention a little bit like Labelle or poly fitting or the rare refinement fitting, right? And how those different approaches actually can also give us the different information. Okay, so this is the slide I just added this time. I think they're still try to correlate this three important aspects with their scientific study we normally do, right? We study on the batteries, either lithium or sodium. So for example, for the lattice parameter, we just experienced how important this can be, right? The lattice parameter helped us to differentiate what we saw is really lithium hydride or lithium fluoride. So actually the judgment was based on the lattice parameter, right? But surely we can also do more systematic studies, like actually in the previous lithium hydride paper, we used the Institute X program, right? And so actually we can have more confidence, but the point is we never can underestimate the importance of lattice parameter. And a very good way to obtain this is to the Labelle or the powder fitting, which is a structureless feature. So so even though this is a fundamental based, but still we have to mention some of the application side. So I think in the future, probably we'll cover the points about why we do the Labelle fitting or the poly fitting, or when we should do the raw refinement, right? So I think we'll cover those practical points sometime in the future. For intensity, I also want to mention there are people who do their X-ray diffraction in the battery community also use intensity a lot for important findings. I didn't include the reference here, But I just want to mention a long time ago, I think it was around 1990 or something, Delmas was actually starting the lithium nickel oxide. So Delmas actually did a lot of work on the lithium nickel oxide. And uh, if I'm not mistaken, I think Delmas probably the first one to propose that actually the lithium and nickel exchange sites. And how did he know that? He knew that because he looked at the X-ray diffraction pattern and he said, hey, if actually there's no mixing, the intensity doesn't match. So as for some specific peaks, actually they showed either abnormally large or abnormally small intensity, which can only be explained because there's a mixing happen. In other words, we have some transition metal in the distant side to account for such kind of abnormal intensity. So that's the basis. So people talk about the lithium nickel kind of mixing all the time. We're talking about for decades, but I think we should give at least give Delmas the credit that actually he used the actual diffraction intensity to really propose this idea, was I think which was identified to be correct by numerous research later, right? And for the peak shape, uh, so as I mentioned, sometimes we see some very unique peak shapes. Then don't just let it go, right? We can decide whether we want to go deeper or not. But once you see something that gives you a hard time to do the fitting, then probably you're seeing something actually very meaningful. You probably there are some very unique features. For example, if you see a very asymmetric peak, then probably that's an implication of that we have a lot of stacking force in the system, right? Then you can talk to other people to help you to really confirm this if you really want to invest the effort. So for example, you can ask a Rochen to do the TEM, right? And so actually stacking force can be easily seen in the TEM and to confirm whether your congestion is right or not. And also, if you sometimes see some exotic peak shapes, for example, if you see some of the peaks are pretty wide and some peaks are very narrow, they kind of are alternating, then just don't let information go. And they're embedded with some very rich information about the system you want to investigate. And I think I will just go through this one very quickly. This is about peak position. Everybody knows we do not have to spend time on it. The Bragg's law, right? The reflection picture, and also this is a scattering picture. The one thing I want to emphasize is that while this one is very convenient, right? It's easy to understand, but relying on this one really cannot help us to go any further. But instead, the physicists always rely on the scattering picture, saying that we have actually incoming X-ray, which is actually a wave, so it has a wave vector, and is scattered by the electron or by the atom. So actually, this is a scattered wave, right? This is a scattered wave. Then there's a momentum change. The momentum, actually, this is elastic scattering, so you see the magnitude is the same, but it's actually a direction change. So there's momentum associated with kind of the scattering. So this is actually the scattering vector that the physicists always talk about. I do encourage, or maybe to put it more seriously, I do require you actually to really to look at all the things from this picture, right? This is the real picture that can take us to go deep and take us to go further, to go far, right? To really understand what's going on. So this picture should be embedded in our minds whenever we talk about the diffraction of the PDF. We are the electron atoms scatter the incoming waves, and we have associated scattering vector, right? This is also known as Q. And also you see the benefits of using this picture. We gain more insights about the real space and reciprocal space. And this is peak position is relating how to see to that parameter. I think everybody understands. We do not have to spend time on this. And peak intensity, and this equation is kind of a formula that is really explaining each specific component that contributes to the intensity we finally measure. So I think the first one is definitely the most important one. As I mentioned, this is a structure factor. This is actually this is equation of the term that takes into account their specific crystal structure. So this is what we really we care about, right? So in order to solve the structure, we need to have accurate F. But what we cannot directly measure F. What we measure is actually I, the intensity. Then we need to understand the contribution from other components so that we can really arrive a very accurate number for this F. And with a set of F, note that F is HKL dependent. So depending on the specific HKL, this F can depend, right? So that's actually the major reason why we see different HKL have different peaks. So once we have a set, actually the more the better, right? If we have like tens or even hundreds of HKLs with their specific HFs, with their specific Fs, we have much more confidence in solving their crystal structure to obtain the position of atoms, right? But to solve F, we need to understand the multiplicity, the Lorentz factor, the atomic displacement factor, and absorption coefficient. We need to understand them so that now we know how to get this accurate F. Okay, and there, as a note, so sometimes the system may have the texture or the preferred on rotation, and also it may not be just a one single phase, actually could be multiple phases. So this can also influence peak intensity, but that could be a more actually complicated, more in-depth lecture on this. So the first one is the structure factor. I think I mentioned this term several times already. And so I just want you to really have a deep impression about this structure factor. It's really, really, really important, and we really need to understand it. Basically, is to simply put, it's basically summarizing the contribution from all the atoms in the unit cell, and which is actually expressed by this term. And we can look at this term, and as we see here, this is basically saying actually each atom is contributing one part, which is amplitude. The other part is the phase. So we need to know that actually so this HKL is actually the complex number. It's not a real number, you see, right? So you see this kind of a phase, you know it's a complex number. And what we really probe is actually the magnitude of this F. So the FHKL itself is actually a complex number. It has this kind of amplitude and the phase. So this amplitude is basically atomic scattering factor of atom J. So if we have a heavy atom, say a transition metal, then we are expecting a very large number for this one, right? But we also need to keep in mind this Fj itself is not a pure number. It's actually a function, and this function is depending on Q. So that's why at the different two-seater, actually the contribution from the same atom can be different. We'll talk about this later. But you need to keep in mind, this Fj is not a number. It's actually dependent on the Q, or on the scattering vector, or on S. So this S is a scattering vector we just mentioned, right? So we from this time on, we always think about everything in terms of the scattering picture. We have the incoming X-ray, which is a wave vector, and it's diffracted by the atom, and then we have this kind of the change of momentum, and which is actually we termed as the scattering vector, either S or SQ. And then we have this atomic coordinate of the atom. This is really the important part, right? So we see the information of atomic position is embedded in this term. And this term enters into here, and then enters into the F, and then enters into the intensity. So we see the correlation, right? There are several steps, but we'll see finally actually the intensity correlates what we're interested in here, the atomic coordinate of atom J. So this XYZ determines the phase for this specific atom. And also we can see this is also the scattering vector dependent. So this number is actually dependent on both atomic position and also scattering vector. So that's why at a different HKL or at a different scattering vector or different two-seater, I think we need to have a change, a notion of change of notion. We'll speak less two-seater. We'll speak more of and more scattering factor, right? So, so at a different scattering vector, actually this phase can be different for the same atom. But this is a picture we need to have. So, and this is actually kind of they're written out in their more complete form, and this is the exact phase expression. So we see the coordination number x, y, z enters into here, right? And remember x, y, z are the fraction coordinates, so they're always like 0.2, 0.1 something, right? So they're fractions, and we see here HKL. So that's the specific peak of the HKL peak we're observing. And those two, XYZ, HKL, that determines this part, and together they determine the phase of that atom. And together with the amplitude, they are summed together and enters into this final formula for their structure factor, right? Okay, so this is I would say the very important equation. And so if you find a mass sometimes can be bothering to you, it's okay. You simply just leave it here and look at this from time to time. After some time, you'll be used to this kind of equation, and you start to appreciate the value of this equation, right? Despite of all maybe seemingly the mathematic the complications. Don't be bothered by math. And there's some notes here. So one thing is, due to translational symmetry, this part actually can be zero. So why is that? I think you can probably even intuitively think, so once we have X, Y, Z, the translation means that we'll definitely have another atom, exactly same atom at different position. For example, if it's a phase center, then we'd have X plus 0.5 and Y plus 0.5 and Z is the same, right? So that would generate another atom. And when you sum those terms together, those kind of X, Y, Z can sometimes cancel out, right? You can imagine how their mass works out in your mind. But the conclusion is, because of this kind of translational symmetry, this term sometimes, when you summing them together through all the atoms, they can vanish. They can go to zero for this F, right? So if the structure factor is zero, then the intensity is definitely zero. So that's associated with the systematic evidence. We'll show a specific example later. And also, as I repeated the saying, the amazing part of X-ray diffraction is the solving structure to know the specific position of the atoms. And that's actually everything hinges on this kind of a correlation between the structure factor and the atomic positions. And also we know the sensitivity of XRD, right? So we see this amplitude part is proportional to the atomic number. So if we have large atoms in the system, that's more easily to be seen by X-ray, right? And for light atoms, then we meet challenges that because this FJ, the atomic scattering factor, is proportional to the atomic position. And so if we have light elements, then how to do that? Then we can turn to neutron, because in neutron, this Fj is no longer proportional to atomic position. It's actually aperiodic. So we have some chances of have a very large Fj for some light elements, for example, oxygen. And oxygen can be a very heavy neutron scatter, or for some like a deuterated the hydrogen. So depending on what elements we work with, we have some chance of actually identify them in the neutron, based on actually their aperiodicity of this FJ term. Okay, atomic scattering factor, and this is a little bit more in-depth physics, and hope this will not turn you off. And but I think this is regards to the physics picture we always need to have in our mind, right? We We may not need to be clear about each detail steps, but the general picture is X-rays scattered by electrons, right? And starting from this very basic fundamental assumption, then people can derive their scattering power of an atom by actually doing the integration of based on the electron density. So this rho is actually the electron density. And also people can go further because this picture is correct. And people can further, and people say, okay, I can learn what's the real electron density of this because I can do the calculation of electron density based on the quantum chemistry, right? So based on the quantum chemistry, people can calculate very exactly, very, very accurately, the electron density of a specific atoms. So we know specifically what the rho or this rho is. Then people do this kind of integration, and actually they can tabulate their contribution, all a specific atomic scattering factor for all atoms across a periodic table, right? And so this is an example for the lithium, since lithium is much easier, only having 3 electrons. So the lithium is easy. So this one is showing an example, but we can see some interesting results here. And those results, I think they're important and they're worth remembering, right? So one thing is we can calculate the atomic scattering factor. Remember that factor is a function of the scattering vector. So this is a scattering vector, right? So you see the 2-theta term. As I mentioned, we do not want to talk too much theta. We always try to use a scattering vector. So this is basically a scattering vector. We see this atomic scattering factor is actually dependent on this scattering vector. It's kind of a, there. I hope to not get you confused, but you know what I mean. So this is changing, and you see the K electron, which is the inner shell electron. In fact, is not that sensitive. This change is not sensitive, but this EL, the valence electron actually decays quite a bit. So overall, we see this kind of a decay of atomic scattering power as the 2-theta increases, or we say as the scattering vector increases, right? So this is an example of using the lithium atom, but this is also valid for all the atoms. So let's say we talk about the cobalt, nickel, and we can do the same thing for let's say for the KH, for the LH, and we will see something similar. And over the overall trend is also the scattering power of cobalt or nickel will decay, and as we go the higher and higher in the scattering vector, right? Or as the higher and as the 2-theta. So this is the important conclusion we need to know, and we need to keep in mind. Also, we understand the limitation of the X-ray powder diffraction, because in general, all atoms will actually make less and less contribution to scattering intensity because their scattering power is getting weaker and weaker for all the atoms. So we always see the very weak peaks at high angles or at high scattering vectors, right? So once you have these weak peaks, so one thing is you will definitely face the problem of a low signal to noise ratio. So signal to noise ratio is the basis of obtaining the accurate intensity, right? So that's one of the problems. The other problem is, so for measuring the PDF, which basically is also based on elastic scattering, and the contribution from each atom is also follows this kind of picture, and the scattering of them toward the end, toward the higher 2-theta, they can also become weaker, and this will cause problem for doing the Fourier transform. So that's why we always need a very high flux synchron radiation to do the PDF, because only a very high flux radiation can guarantees we can still have a very high quality signal to noise ratio peaks at even high 2-theta angles without the limitation of this physics picture, right? So even though you're decaying, but because the radiation is so strong, we can still clearly see their high angle peaks. They are very important. So that's the justification why we want to really use the high flux radiation for doing the PDF work. Okay. And the note here is that For neutron, um, we need to keep in mind, because for neutron, it's the radiation is no longer interacting with electrons, right? So it's actually interacting with the neutron. So it's a totally different physics picture. And in that picture, they're scattering from each atom, or more specifically, from each nuclei. They do not decay as the two theta increases. So this kind of intensity will be flat if we're talking about the neutron. So that's one of the benefit of using neutrons, since you can enhance the high angle peaks, right? And which can be very important for solving the structure. As I mentioned, more peaks, accurate intensity, those are keywords to really to get enough information to solve the structure. And the neutron have definitely the advantage in that sense, right? Okay. Okay, systematic absence. I think probably this is also covered maybe in the in graduate or undergraduate courses. Uh, so and also actually we do not use systematic absence that often, but I think it doesn't really harm to really understand what it is, right? So the general picture is that once we have this kind of translational symmetries in the system, then it's likely that we can induce the systematic absence. So I want to remember this keyword, translational symmetries. And this relates back to some of the fundamentals about the space group, about reading the international table of crystallography we had before, right? So you see all those things are connected. So the time and effort you invest in understanding one aspect and can have actually a fruit in some other aspect. So if you really understand the space group very well, and you really understand the symmetry, the language of the symmetries, what those symbols are, what they mean, right? And then you have this understanding of actually the XRD, specifically the systematic absence, which is really related to translational symmetry. And translational symmetry includes this, like the phase center. So what I mean by this one has translation symmetry is that, so let's say, look at this is simply the FCC. This could be a nickel, right? So all the copper, which are all the FCC structures. So for example, if this is nickel, and we have an atom here, this is 000, right? So this is 000, and because this unit cell have F M3 by M symmetry, starting with F, that means it will definitely have a symmetry equivalent atom here, here, and here. Those are all the phase centers, right? And they must be exactly the same atom as what we have here. And you can be more complicated. You can say, okay, I'm not about talking about atom. It could be like some molecular motif, right? For example, this could be like titanium sulfide or something. For example, just for example, then if you have a molecule here, then you must have a same molecule with the same identities, the same orientation here, here, and here. Everything is related by translational symmetry. So that's what I mean. F have this kind of a translational symmetry. And specifically what that means is that if this atom, say, is not 0, is say the atomic position is XYZ, then I can tell you must have another atom of exactly the same identity as like X plus 0.5, Y plus 0.5, and a Z, right? And the same is true for other three atoms. And you can do the same thing, go through this something similar in your minds about the body center, right? If you have something here, you must have the body center. For example, lithium metal is actually body center. It's IM through IM. So once we have this in here, we must have a lithium in the body center. And they are related by symmetry. And also the glide planes. If you still remember what glide planes are, if not, you can check the lectures we previously had. I think we talked about glide planes, right? And we specifically talked about the D glide, which relates to the diamond, the glide plane, right? So yeah, just spend some time understanding what they are, and their screw axis, right? Depending on their system, sometimes we have this screw axis. I'm sorry, there's a chat here, right? Need to receiving just reminder of yourself 4 p.m. See, don't get talk. Okay, yeah, Chin just left a message. There's a 4 p.m. meeting of a CFN colloquium. It will be given by Gersider from Lawrence Berkeley and Berkeley. So yeah, if you're interested in that talk, you can join. It's a CFN colloquium tomorrow at 4 p.m. If you do not have a link, you can type your request here, right? And I think somebody who has a link actually can just paste the link so that everybody knows.
Yeah, I'm still here, but I may leave early. So in case.
Oh, I see. Watching you still here. Okay. Yeah. I didn't. Yeah, I didn't see the camera. So yeah.
Okay.
Okay. Maybe I'll finish in 10 minutes, something, so we can limit the talk to this lecture to about 1 hour, maybe. Yeah, so this one is basically our example. I think probably this is also showing some of the textbooks. This is is showing how FCC lattice can give a rise to the systematic absence, right? So we have the translational symmetry, which is F here, and there we can see after some, I think it's a pretty simple, straightforward mathematical derivations that we can arrive this final term, right? And we have the magnitude and the phase. Hope you can still recognize them. And specifically in this phase term, we have this h plus k and k plus l and l plus h. And then we realize that only when they're all zero, right? And can actually this term will no longer be not be zero. Otherwise, we will have -1 here and plus this one. The whole term will be zero, right? To avoid that, this three terms cannot be added up to -1. And the guarantee of that is only comes when HKL, they're either all odd or all even numbers, right? So for the FCC system, so we typically see peaks like 200, like or 111, or like 240, right? So those kind of peaks belonging to the FCC, we will never see any peaks like the 112. Those peaks will not happen in FCC because this translational symmetry will give rise to this kind of a systematic absence that requires the HKL have this kind of a relationships. Okay. I'm moving. Okay. So I think I have 10 minutes to finish. So maybe this is the last one we are talk about. This is a specific case. And I just want to give example of using structure factor to analyze the XRD peak. And it's very specific to the battery research, right? So I think everybody probably can recognize the structure of lithium manganese oxide, the spinel structure. So we have the lithium residing in the tetrahedral site, and we have the manganese residing in octahedral site. Especially if you look at this manganese, right? It is actually coordinated with the 6th oxygen, and there is forms of octahedral. So this is spinel phase. And if you look at the literature, and you probably will see a lot of times, and people sometimes would measure the XRD and say, hey, I have a large 220 peak here, right? And then what they say next is, so according to the reference, then they relate to another reference saying, hey, that's what they say. They always say, if you see a large 220 peak, that's because you have the transition metal taking the lithium site. So that's kind of the argument in the literature over and over again, right? But so if we understand a structure factor, really can answer why this is the case, right? It's simply based on the structure factor analysis. And also, by the way, this is based on the F cubic. This is the FD3 by M. I think we also talked about this specific space group last time when we talked about the space groups. Things actually have the dissymmetry. So we talked about the how dissymmetry sometimes show up in the battery materials, right? So we took this as example. And also, this is a FD3 by M. So it starts with F. So you see this is the cubic based, the F lattice. So because this F, So we see the HKL can only either be all odd or zero, right? They are all odd, I'm sorry, all odd or even. So this all even, all even, all odd, all even, all odd, all odd, all even. But in fact, there should be more systematic absences, right? Because actually we have the D-symmetry. And if you remember, the glide plane also is a kind of a translational symmetry. So we have D here, and that will eat up some additional peaks, right? So we should be expecting fewer peaks than some just simply the F, their qubit system. So you can already apply the knowledge we learned to really look at this pattern. Okay, back to this intensity, 220. So why the increase of 220 means the migration of transition metal, right? So we can actually really do the calculation. So I hope we do not actually be intimidated by their long list. This can be very simple to do. You can just use Vector to Vector can give you all the atomic coordinates in the structure. So if you input the spinel structure into Vector, and Vector actually will list all the atomic number the positions for you. So you see this lithium is in 8A side, right? So if you look at this Wyckoff position and you still remember what A means, what 8 means and what A means, and you already appreciate, okay, that means there are 8 lithium atoms in a cell, and they have their own specific positions, right? And by the way, actually, they are all generated by this first one simply by their symmetry. And also we have the manganese, which resides in the 16D site, right? So we have 16 manganese atoms, and we have 32 oxygens. Don't be bothered. You can just list all of them in Excel. And then you can do the calculation based on this formula, right? Since everything is known here, you know the F, J, F, you simply just for the sake of simplicity, you just use atomic number, right? Even though it's actual function, you can use atomic number to replace this one. And this one, you know the HKL, right? For the specific peaks, and also you know the XYZ. So you can summarize all them together. You can do this simply just use the function in Excel and to the summarization of all the atoms in the one unit cell, and then you reach this structure factor for all the HKL peaks. And specifically, we can look at the 220. We see that actually the contribution from the transition metal is muted out. We do not see any contribution from the transition metal because actually it's muted out by the symmetry. Only lithium and oxygen contributes to this 220, right? So that means if this term actually somehow grows larger because we have a transition metal here, you can imagine how much the increase could be, right? Because lithium is a 3, transition metal can be like a 25 or 26. So that would be a lot of increase in this term, and that would lead to the increase of the structure factor and also the increase of the peak intensity. Right? So this is the basic argument why 220 can be an effective indicator for such kind of intensity increase. And for same reason, you can do this with the 422, right? And then you can see 422 is also very sensitive, right? Since actually the transition metal is also muted out. So it's also very sensitive indicator whether there's actually heavy atoms in this site or not. And you can even go further. You can even revisit actually the analysis of layer structure. So let's say look at the lithium nickel oxide, and we have the 3A, 3B, and the 6C side, right? You do the same thing for all the HKL, and you analyze what atoms really contribute to each peak. And it's possible that some peak is only contributed by only certain atoms, not all of them. And so actually you have some atoms muted out in some HKL peaks. Then you can analyze, okay, if this peak intensity changes, what could be the possible reason, right? So I think that's the useful part of this structure factor. And this is dates back one of our previous paper on AFM. I think well, already 8 years ago. So so this is actually the in situ XRD analysis. Yeah, I participated in this work. Actually, I was mainly responsible for writing the analysis of in situ XRD. So so actually the scheme used at the time actually is based on structure factor analysis. And if you have time, if you read this paper, you'll see that we not only explain how the intensity changes, we also predict, based on this kind of analysis, predict when the oxygen release will happen. Because actually when oxygen release happens, the framework is damaged. So actually the analysis based on the same structure assumption is no longer valid. So all those details actually relates to the structure factor, and you'll see we can really analyze a lot of things from the in situ data. Okay, so I think we'll end up here. We can go further next time. And if you have any questions or comments, just let me know. Thank you.